Continue? Yes. All
Yes,
right. So
please.
I'm going to talk about linear accelerator. I must say that I'm very pleased and honored to come after the presentation of Heidelberg, as I was a Heidelberg PhD in the old time. So that's a nice link for me. So talking about LINAC, I have to make a disclaimer first of all. So most of the lecture will be on Hadron Linux, also because it is related to this application of Hadron therapy as the school is. So Lepton Linux have many similarities. So most of the things that I will talk about are can be applied to Electron Linux as well, but also a few very important differences, which I will highlight very quickly afterwards. So here you see not the Heidelberg Hadron therapy machine, but the CNAO atom therapy machine in Pavia, which Marco Puglia will tell more in the course of this week. So highlighted up there, you see the injector. So in my definition of the LINAC, the LINAC is the accelerating part of the injector, including the RFQ, what is not included in, for example, in CNAO terminology. So it's the part where the beam really gets accelerated. The injector itself includes the ion source and extraction from the ion source and the low and medium energy transport systems before and after the LINAC. So Nadia Gambino yesterday gave a very nice and comprehensive overview of ion sources. So I'll be very quick on these. So an ion source is some types of ion source may be viewed as a plasma, what is called the fourth state of matter. So a hot ensemble of electrons and ions, of which you optimize heating, confinement, and loss mechanism, and you produce your desired ion type. Actually, you remove the ions from the plasma, from the mixture of electrons and ions, through an electric field at the hole. So the extraction voltage may be in the order of 30 kilovolts. If you need to be very energetic at the beginning of the LINAC, what might happen depending on the design and the circumstances, you might even put your source on a high voltage platform, which might have a voltage around 300 kilovolt, more or less. So that can be a big boost to the energy of the beam at the very beginning. This is actually the injector, which drives the beam from the ion sources in the CNAO case to the LINAC. So indeed, I don't want to bother you with the importance of the Lorentz force. I think you heard a lot by both Maurizio and Marius in the past days. It is actually the essential formula, the essential force. And I would say that if you know it well, really well, you can build up most of the formulas together with special relativity, which help you building an accelerator. I wanted just to point out that indeed, I said that I cover only the accelerating part of the injector, but of course the first boost of acceleration, as I said, you get from the ion source, and it is necessary not only to transport the beam at the beginning of the LINAC, but also it allows the low energy beam transport line to accomplish the very important function of selecting the A over Q, so the mass over charge state of interest from the ECR ion source. So by using the dipoles in the dispersive mode, you are able to select according to this formula, which is coming from the Lorentz force and some simple kinematics, the appropriate radius which selects the A over Q and dumps the others on the slit. So rejects the contaminants before they might get accelerated, and they may be disturbing, of course, because they are coming to the patient, and it can be disturbing, for example, the cure of heavy ions. So in the following, it may happen, and it often happens, that when I talk about Q, I talk about Q times the electric charge of the electrons. So I give my apologies. It is a confusion which is often made in our field, and I am also a victim of it. So as you've been told already, after an injector, you may really very well continue the acceleration and give the acceleration boost with an electrostatic accelerator. Of course, you know already that we have limits of maximum voltage in the terminals of the electrostatic machines. What I wanted to point out here is the maximum energy which you may achieve with these electrostatic accelerators, which you get with tandem Van de Graaff accelerators, which we use, for example, still routinely at NFN since decades. So in this case, you may inject a negative ion beam. So you add one electron to your neutral atom, you inject it into the tandem. It sees a terminal voltage which can go as high as 16 megavolts, so a very large terminal electrostatic voltage, which you can achieve in high pressure insulating gas. And a negative ion is extracted by the terminal. In the terminal, with a given velocity, they find a stripper, a gas or a stripper foil, which strips these additional electrons and a lot of other electrons. So downstream the terminal, you have a charge state of several plus, maybe 10 plus, 12 plus, depending on the ion and other parameters and other parameters. And so you actually repel the positive ion from the terminal at a very high voltage. So final energy may be 16 megavolt times 1 plus Q, which is a relevant energy, which is of interest for several accelerators, for several nuclear physicists, for example, or applied physicists for their research. Eventually you run into sparks. Of course, you cannot exceed the accelerating voltage, the terminal voltage, beyond a certain extent. So what you need to go is that taking again the example of the tandem, you may switch from changing the polarity of the charge from negative to positive to changing the polarity of the electric field and repeatedly along the beam path. You have already seen the concept of the Widero drift tube Linear. So the particles are subject to a synchronous accelerating voltage and experience an energy gain at each gap crossing, which is given by the product of the charge state times the delta V that they get at this voltage. Then indeed the Widero drift tube Linear sees the drift tubes enclosed in an enclosed cylinder, metallic cylinder, and resonant with, so the electromagnetic field resonate at given frequency. This improves the efficiency of the creation of the electromagnetic fields, the level of the electric field along the ion beam path, and as Marius said yesterday, Marius Sapinski, it avoids dispersion of RF waves around. So you see the Linear 4 DTL, which has been shot by Maurizio here in the picture. In order to accelerate a beam with a Linear, not with an electrostatic accelerator, you can accelerate a continuous beam, no problem. But in a Linear, you need to have the beam bunched. So indeed, between one drift tube and the other, you must have a bunch of particles concentrated in space, which sees a shape of the field like the one which is depicted here. So increasing at the center in Z, and which changes from the maximum to the minimum in time. So you must be very careful that you synchronize your bunch of particles with the field being around the maximum of the accelerating field when the bunch is around the center of the space in between the drift tubes. And of course, when you accelerate here, you have got the decelerating field in the next drift tubes. So as long as the particle drifts in the drift tube, which is sort of Faraday cage, the field changes phase with the RF phase, and you get it accelerating again in the next drift tubes. So by the sequence of these drift tubes, you get a very high level of acceleration. As you may see, that at each gap crossing, you increase the velocity. So keeping the frequency the same, the length of the drift tubes, as you saw, must be increased. And actually the formula may be something like this. It is always proportional, let's say, to the product of the beta, which is the velocity of the particle divided by the velocity of light, times the wavelength of the RF, which is the velocity of light divided by the frequency of the radio frequency. Each gap crossing. Actually, if you play with the Lorentz force, I said that the Lorentz force is a very good guide, but you have to play mathematically with some physical ideas with it. If you play quite simply, I would say, with the Lorentz force, you come with an expression of the increase of kinetic energy at each gap crossing, which is just the product of Q times the V0 T and cos phi. So Q V0 is actually the same energy that you would achieve if you had an electrostatic field in between the drift tubes. Phi 0 is the phase of the bunch at the gap center. As I said, it may be at the maximum or at a lower value of the field which is changing in time. And T represents is a number which is always smaller than 1 and accounts for the fact that during the gap crossing, the voltage changes in time as long as the bunch crosses the gap. So it is just this simple formula. So if you take, just to give a number, a superconducting resonator like the one that you see here, which is just 20 centimeters in length in the direction of motion of the beam, and which can achieve an accelerating field of 6 megavolt per meter, for example, the delta V is, which you get is 1.2 megavolt, which you can compare with the 16 megavolt of the electrostatic accelerator. So with just 13 resonators, you do what a tandem Van de Graaff does, and you are not limited, so you can do it as many times as you want. We can say that the limit is length that you have available, or the money that you have in your pocket, or the need by the physicists. The choice of the phi zero is very important. You have seen it already, that if you depict the energy gain versus time, or versus phi, which is equivalent, actually you have, of course, you need to accelerate in the positive and not in the negative part of the deceleration curve, accelerating voltage versus time. But you have to choose also your phase very cleverly, so that you have, if you have a bunch of particles which is centered around the green particle here, in this part of the curve, the particles which are not in the center of the bunch are, let's say, oscillating around the bunch center from a gap to another. Then we can come again to this concept. It is not, if it is not very clear, but I think it has been explained a couple of times already. Whereas in the other parts of the curve, either you have a decelerating field or an unstable field. If you give power to a cavity, RF power, then this power is coming from RF power sources, which transform the electrical power from the electrical network into RF power, which you can drive through waveguides or coaxial cable, whatever, depending on the frequency, depending on the power level. You drive them to the cavity, and you couple to the cavity through an antenna, which you call a power coupler. So this line and the coupling to the cavity has to be studied in a careful way, so that the power is transmitted very efficiently to the cavity itself. So you create electromagnetic field in the cavity, which create an accelerating field along the beam line. So you have these different kinds of RF powers for your power sources, and for the different frequencies you can choose different kind of power sources. And you can see that in the CW mode, this can be actually gigantic power sources. They can go as up to 1 megawatt of power in CW mode, and tens of megawatt in AC mode. If you use this RF power to feed RF power to the cavity all the time, as I said, is very expensive in terms of power that you get from the source, in terms of also of the bulky size of these amplifier systems, and moreover they heat up the structure considerably. So they force you to design big water cooling schemes of your poor cavity, which is devastated by this gigantic amount of radio frequency power which is arriving. So indeed, what you do is to keep the RF power for barely the fraction of time, which we call the duty cycle, the fraction of time which is required by the users, unless you use superconductivity, which is relaxing a lot this concern. So at CNAO, or a typical heavy ion therapy facility, for example, you have an RF pulse of half a millisecond every 100 milliseconds, so a duty cycle of 0.5% only. Within this 0.5%, so these are the RF pulses, very much distant in time. Within an RF pulse, you have all the oscillation of the RF frequency. Don't be confused between the RF pulse and the, let's say, the oscillation of the RF. The RF pulse may be as long as I said, 500 microseconds, and the oscillation of the RF 5 nanoseconds, so much shorter, and they contain all the bunches that you want to accelerate.
No, estás semana solo.
I see some noise in the background, so maybe you should switch off your microphones, I think. Okay, so the two main pathways to design a LINAC has to deal with two, let's say, sort of separate sciences. So the one of cavity designer and the one of beam dynamics designer. So in the cavity design, you control the field pattern inside the cavity, so using 3D electromagnetic simulation codes, basically. So you want to concentrate the electrical field along the beam line and maximize the accelerating voltage here and minimize the dissipated power on the walls. So what you want to maximize are parameters like these, so like the so-called shunt impedance or the Q value, which are maybe ratios. You see that in the nominator, you have either the stored energy in the Q definition or the square of the accelerating field in the shunt impedance definition, and you have the dissipated power at the denominator. Indeed, the accelerating voltage is limited still by electrical discharge with a phenomenology which is very similar to the electrostatic accelerators. And the dissipated power is limited by the cooling capacity of water for room temperature cavity, or by the critical temperature of your superconductor, which might be niobium or others if you have superconducting resonators. The beam dynamics people have to control the synchronization between the field and the bunch, so design a beam in which the synchronization is very carefully depicted, and ensure that the beam is kept in the smallest possible volume during acceleration. And it is far from easy task, as you will appreciate. So they work in these so-called phase spaces, which I will define better in a moment. So they describe the beam in the spaces which are transverse to the direction of the motion, and in the phase space which is along the direction of the motion. And here X is actually the X, so the transverse horizontal direction, and Y the Y horizontal direction, and X prime and Y prime are the variation of X along the direction of motion. Coming back to the design of cavities, once you use the 3D electromagnetic modeling structure, then you build a structure, and structures can be made in copper. They are mostly made of copper. And this copper is a very easy and very convenient material, which is a little bit soft. So it is often braced to an external cage in an external structure in stainless steel. And the material is, let's say, a standard for low velocity and low duty cycle cavities, and not only, because it is cheap and reliable. You resort to superconducting materials and superconducting cavities, and to niobium, and you have to go at very cold temperatures for Kelvin, beyond the let's say the minimum temperature that you achieve in nature, which is minus 273 Celsius. Only if you have to go to very high accelerating field, or if you want to concentrate a linac in a decent length to achieve a very high energy of the beam, or if you have a high duty cycle, as I said before. But then you have to encapsulate your superconducting cavities in so-called cryostats, so these containers, sort of thermos, which insulate your very cold cavities from the room temperature environment which you have around. And this is a bulky, let's say, technology which has a lot of difficulties to be built. But actually, it is the only solution if you want to build very powerful linac and also very powerful synchrotron in some cases. So just before going to the beam dynamics, I just recall you very briefly some concepts which you saw already. So no matter how much you increase the kinetic energy of your beam, which you do with increasing the energy in an accelerator, you come to a point in which you approach the velocity of light, but you never overcome it. So you must use formulas. That's why special relativity is important for us. Very simple, I would say, special relativity in a way, because classical relativity will drive you far away from this real condition, which you find in nature. So if you reverse the graph, it is a graph like this. It is just a little bit of a change of the classical Einstein formula, E equal mc square, in the sense that with moving particles, you had your factor gamma, which is just this function of the ratio of velocity of the beam to the velocity of light. Among others, you see that it is much easier to increase the velocity of electrons with electric fields than of protons and heavy nuclei, which are much more massive, but still they both approach the velocity of light without crossing it. So in the design of particle accelerators, this must be taken into account. Another very important concept is that of the harmonic oscillator, which describes in general basic stable motion in many phenomena of physics and also outside the physics domain. And this is given by the very simple formula of the spring, and which translates by playing with the Newton formula F equal ma into this very simple formula of the equation of motion for the harmonic oscillator, which you will see it again in the next couple of slides. So transversally to the beam direction, then you have to cope, as you saw, with the space charge of the beam. So the bunches indeed can contain many particles, 10 to the 10th or more even in some cases. So they suffer from the Coulomb repulsion between the particles, and they are repelled from each other. This is not completely true, because if you see, for example, this tube of particle in a portion of your LINAC or your accelerator, and you see a particle with a black dot up here, this particle indeed sees a lot of charge from the inside of this cylinder, which gives a net acceleration, let's say net electric field towards the outside, so the Coulomb repulsion indeed. But it experiences also an attraction given by the magnetic field. Which magnetic field? So the magnetic field which is given by the current of the beam itself. So the beam has a current E, and the current E, as you saw from the Lenz law, introduces a B field all around the beam. The field is in this direction, transverse. So the vector product in the Lorentz force of the velocity and the B field gives a force which is towards the axis of the beam. So there is a competition between the two, which at very high energy cancels completely the space charge, but it does not at very low velocity. So the net effect of the space charge is this formula here, which I did not derive. And you see that it is very high, the space charge force, at very low velocities, at very low size of the beam radius. This function is even quadratic with the inverse of the beam radius, and if you have high currents of high charge states. So you must be worried, particularly at the very beginning of the acceleration. And the very beginning of the acceleration is a portion of the LINAC, which is very critical and which I will cover at the end. So then you have to, not to fight, but to cope with the space charge, as Mario Sapinski showed yesterday, providing a sequence of alternating focusing and defocusing quads, and you do also in the drift tubes of a drift tube LINAC by inserting magnets in the drift tubes, and you got a sinusoidal variation of the envelope, which stays, let's say, in general, as a macro effect focused. If you play again with the Lorentz force, sorry for that, this is not a very long derivation, so it comes relatively easy. Then by playing with the Lorentz force, you come with the general equation governing the transverse motion of particles in the accelerator, which is a formula like this. And you saw that the result of the formula is this one. And you have been told already that along the LINAC, the particles are confined in the elliptical areas in the x prime phase space. With x prime, again, I repeat, it is the variation of x along s or along z. I will confuse the two terms, which in the LINAC can be synonymous, actually. So this is the direction of the beam. So you see that this is not too awkward. So this so-called Hill's equation governing the motion in the transverse space is very similar to the equation of the harmonic oscillator, very similar. So the only difference is that K is actually changing along S, so along the LINAC. So as you say, the definition, even in Wikipedia, it's a system which, when displaced from its equilibrium position, experiences a restoring force which is proportional to the displacement. So it is a very stable situation for the ensemble of particles. So not only the center of your bunch, not only the center of the beam along the beam axis, but also particles reasonably around it experience a restoring force. And if you go a little bit farther with the spring, you see that if you depict the displacement of the spring versus the velocity of the same displacement, indeed this stuff here, so the weight, is following an elliptical path in this graph, which is actually the phase space. So no surprise that particles behave along elliptical trajectories also in the accelerator. Indeed, I said that there is a difference. So Ks, which is let's say the spring constant, is actually it's not a constant. It's changing along the Linear, and so does the shape of the ellipse. If the ellipse changes the shape, also the let's say elliptical motion of the particles will be deformed in a way. And also this is the amplitude of the motion of the particle in the ellipse. So it will change along the Linear. So you'll come, for example, from a converging beam in this example to a waist, so a minimum of the size of the beam, to a divergent beam, etc., etc. So this amplitude of motion is the amplitude is a square root of a function which is beta, which is not the beta v over the velocity of light. This is rather confusing. It is a function. It is called one of the twist functions of a machine times the emittance of the beam, which is just the area of the ellipse in this phase space. So actually, I said before, and I outlined here, that the harmonic oscillation applies to the three phase spaces, so not only the x prime, y prime, which behaves more or less the same way, but also to the z prime, or the phi energy phase in the direction of motion. And you see it, I cannot derive it analytically, but you'll see it in a second. As you might recall, if you take three particles of your bunch, where the green one is the particle as the center, you will not be surprised that in the longitudinal beam dynamics, so the beam dynamics in the direction of motion, so in the z energy phase space, you have stability in this area of phase or time, if you want, of passage of the particles. I already discussed, and you saw it in several circumstances. So I just tell you that in formulas, which is actually not just a tiny bit, a couple of pages maybe of relatively simple mathematics, just starting playing with the variables phi and w, where phi is the difference between the phase difference of the generic particles on the RF phase minus the phase difference of the center of the beam with respect to the RF phase, and similarly for the energy. Playing with it, you come to two differential equations in phi and w, which you can put them together. You come to the equation of motion of the beam in the phi and E. Actually, it is governing the equation of motion in the longitudinal phase space, because phi is a function of W. Again, it is very similar to the equation of motion of the harmonic oscillator. Here you see that you only have phi, here you only have x, but with a double derivation of x, and here you have a double derivation of phi. So again, really, it is very similar to harmonic oscillator. So not too surprising that, as you saw from Mario Sapinski's presentation, when you switch on an RF field around your synchronous beam, which is the synchronous beam is just a yellow area which you see here in a period of the RF oscillation. At a certain moment, you pick up your continuous beam, you switch off, you switch on the RF, you create a potential well, or a so-called bucket in the phase space, you trap the particles, and the particles start rotating around circles or ellipse in general, at least as long as the motion is close to the center. Outside is a little bit more deformed, so the physics is not exactly the same, but more or less the same. And then once you bunch the beam, you start moving the phase from the bunching cavity to the first accelerating cavity, more or less slowly, from minus 90 degrees, which is the value of the phase which you have here, to the accelerating phase. You stay in the stable range. You restrict the area of acceptance, so the maximum area which is occupied by the longitudinal phase space of the particles. You shrink your phase space, and you start accelerating the beam. Actually, as you see, the phase space shrinks as long as you increase the accelerating phase. And of course, you must find a compromise between the size of your area, which will host a certain number of particles, and the phase, which the higher you go, the more efficient you are in acceleration. Actually, the K in this case is a very complicated formula here, which we can comment long, but I have not time to do so. But a problem which I left you open is how to handle the space charge right at the beginning of the acceleration after the ion source, where the beta is really indeed very low. So the beam dynamics is very tough to solve at very low ion velocities for a number of reasons. The first of all, I told you already, so the space charge force is very sensitive, so it's very high where the beta is very low, so it explodes really, particularly if you have high current beams. So if the beam is negligible, the beam current is negligible, you're not very much worried even at low voltage. But if you have a reasonable current, then you are worried. A second reason is that at low velocity, if you start accelerating the beam with a drift tube, you should find space for your magnet in very, very short drift tubes, which is really very different. That can be really millimeter long. And the third reason is that if you look again at the Lorentz force and this part, the focusing part, B is in general less effective as a focusing function at small values of the velocity, because the force given by the magnetic field is indeed the vector product of the velocity times the field. So if you have a low velocity, even for a given magnetic field, the focusing force will be small. So you would come to the point in which you say, okay, well, fine, the simple solution is that I use electrostatic quadrupoles instead of magnetic quadrupoles. And it is actually a marvelous idea. And this is what we do, for example, at INFN, if we want to transport a low velocity beam for a very long transport channel. We have tens of meters long transport channel with radio frequency, with electrostatic quadrupoles. This is fine, just to keep the low velocity beam focused, but we are, let's say, accelerator people, and we want to accelerate this beam, so it is useless at low velocities. And in order to accelerate it, there is a good point, which has been a very good idea, which was invented in the 70s, which is the RFQ. Indeed, it is a complex system of sophisticated physics and sophisticated and complex and sophisticated engineering, which puts, let's say, everything into one component. So, but the basic idea, however, is not too difficult. So you use a long single electrical quadrupole channel in a radio frequency cavity, where the polarity alternates with radio frequency between opposite electrode couples. So you see here that there is a positive polarity on the horizontal electrodes, and the negative polarity on the vertical electrodes. And you change these with RF. So as long as your beam goes through, the polarity changes, and it is as if you were changing the polarity of a sequence of fixed focusing or defocusing electrostatic quadrupole. So it works marvelously to keep the beam focused. Still, it does not give any acceleration. So to give acceleration, you apply a small but very important deformation on the quadrupole vanes, both in the horizontal and vertical vanes, and you alternate between horizontal and vertical vanes, the hills and the valleys. So you generate a small but very crucial, very important field along the axis in sort of gaps, like the drift tube gaps of increasing length, so increasing with the beta of the particles. Actually, so the RFQ is a very special resonator in which the velocity profile is written in the copper of your structure. And so indeed, by doing this, you accelerate gently, and at the end of the RFQ, you have increased the voltage enough that you can handle it with magnetostatic focusing elements. As I said, it is more complicated than this. So before the acceleration along an RFQ, while keeping the beam focused, actually you gradually, first of all, you gradually increase the transverse focusing. You do no acceleration at all, no bunching. You gradually increase the transverse focusing so that you can trap the beam very well inside the acceptance of the RFQ. And then you start your you're bunching, again, very gradually. So the beam is treated very gently in the phase spaces, x prime, y prime, and phi e of the RFQ, and then you start the acceleration. So by doing a very gentle treatment to the beam, the emittance of the source, which is a very big heritage that you have from the ion source and you want to preserve. So it talks about the density of particles, is very well preserved, and it is delivered as such, so not very much increased to further acceleration. RFQs can be very compact at high frequency, for example, increase the energy of a very small amount, for example, just 1 MeV, and work at very small duty cycles, or very massive, with a very large final energy, and with even a 100% duty cycle. And in those cases, you see those RFQs on the right-hand side, and actually you barely see the RFQ structure in the upper one, and you don't see it at all in the lower one, actually. So the cooling of the structure, for example, is so complicated that the cooling system, the vacuum system, the RF power systems are really massive. So it's a big piece of technology. But let's give credits to Kapczynski and Teplikov from the former USSR, who first invented this RFQ concept in the 70s of the last century, so already 50 years ago, almost. I'm coming to the end. So now you have your LINAC, and I mean, you have your proton or ion LINAC from what I told you about. So you have the essential elements. I told you about the ion source, the low energy beam transport line, the RFQ. I mentioned the medium energy transport line, the DTL, and you might have a number of cavities following the DTL going to higher and higher energy. Indeed, as I said, the ion LINACs or proton LINACs are approaching the velocity of light very slowly, and they reach more or less the velocity of light close to at some giga electron volt. So, and there are very few LINAC existing which achieve this energy. So in general, the design has to be adapted very carefully to the increase in particle velocity. So you have many different types of cavities along an hadron LINAC. If you use electrons, a mass which is 1/2000 the mass of the protons, and even more of the ions, then in just 1 MeV of acceleration, you come very close to the velocity of light. So the kind of structure that they can use for acceleration can be all the same. You have come very close to the velocity of light, but to 1 MeV. So in order to increase the energy of the beam, for how strange it may appear, but that's the special relativity, in order to increase the energy of electrons or positrons, let's say leptons, to very high level, you still need very long LINAC. So the ILC, which is the International LINAC Collider, which is in study since 20 years or more, is actually 31 kilometers long in order to achieve a very reasonable voltage for particle research. LINACs are used for many purposes, both electrons and proton and ion LINACs, for the science of nucleus and elementary particles, for injection to synchrotrons, for radiotherapy and hadron therapy. So in black are the LINACs which can be made of electrons or hadrons for these purposes. In blue, the proton and ion LINACs. In red, the electron LINACs. So you can use proton LINACs to do neutron sources, or to do the transmutation of the wastes from fission nuclear power stations. You use electron LINACs to build free electron lasers for X-ray imaging of very sophisticated precision. You may have industrial applications with very short LINACs for national security, so cargo inspections, for example, for material treatment, material analysis, for ion implantation in the semiconductor industry, and even to sterilize food in the food industry. So there is a huge number of LINACs in the world, the vast majority of which is to produce X-rays for radiotherapy. In conclusion, in the context of this masterclass, the LINAC is the first section of a chain which will eventually delivers a well-focused beam of the desired intensity and size to be scanned very precisely at various energies through the patient's tumor, as you have seen already in the course of this week. It passes to the beam, the LINAC passes the beam to a synchrotron, into which it has to be injected, which is a rather sophisticated phenomenon, which will be covered by the next lecture by Elena Benedetto. As I said, we use the LINAC for a very limited fraction of the available time, so just 0.1% of the time for heavy ion therapy purposes. So it is reasonably easy to provide a LINAC for 10% duty cycle. So indeed, we are investigating of using the remaining time for producing radioactive isotopes for nuclear medicine. And this is a subject which will be covered by a short lecture of Aris Mamaras on Friday. So let me conclude with a very nice picture of the CNAO heavy ion therapy facility, which will be covered in a lecture by Marco Pullia on Friday. And with this, I thank you very much for your attention.
Thank you very much, Giovanni, for this nice introduction and anticipating the next presentations also. So sharing now the Google form. Let's see how many questions we have.
Well, this is a good question. So the LINAC can be used as a standalone for heavy ion therapy. There are studies on these, and also at CERN they are investigating this. You need to have a very long LINAC, so it is disputable if it will be, let's say, economic to do this. So it is one of the options which are on the floor for ion therapy. This is correct.
Okay. As we don't have more, we can be on time for the next presentations, but in general, speakers, please leave some time for questions. And we will take